We are now living in a fascinating era in which we know that the stars that we see in the dark nights, and even the ones that we cannot perceive with the naked eye, are orbited by planets. These faraway planets we call exoplanets. It is natural to think that these exoplanets are also worlds like the ones we have here in our solar system. Are they big gaseous planets like Jupiter, desert rocks like Mercury, or living blue ecosystems like the Earth? You watching this have certainly thought about the latter point. Are there exoplanets out there similar to our home? Is there an Earth 2.0? And if so, where is it and how can we find it?
Nowadays, we have discovered the astonishing amount of more than 4,000 exoplanets. They all have different sizes, masses, and even orbit stars which are not similar to the Sun. Are some of them similar to our planet? First, we need to ask ourselves, what constitutes an Earth-like planet? Is similar size, mass, and composition sufficient? How similar should the atmosphere be? Should it have a moon similar to our own, or a magnetosphere? What about its parent star and the characteristics of the planet's orbit? Where do we stop in our definition? How many similarities are required to call a planet Earth 2.0?
The two most successful methods for exoplanet detection are the transit and the radial velocity method. When a planet passes in front of its star, it blocks a small amount of the light reaching us. The amount of missing light during a transit can tell us how large the eclipsing body is.
On the other hand, the radial velocity method exploits the fact that gravity works both ways. Just like a star is orbited by planets and other bodies because of gravitational interaction, planets also pull on their star. The more massive the planet, the stronger the pull. Thus, a planet doesn't exactly orbit its star. What really happens is that the two bodies, or whatever many there are in the system, orbit their mutual center of mass.
Because of this effect, it is possible to observe the radial or line of sight back and forth motion of the star with respect to us, the observer. This is done by measuring the Doppler shift of the spectral lines as the star travels around the center of mass. When the spectrum is redshifted, the light waves reaching us appear stretched, which means that the star is moving away from us. Conversely, when the spectrum is blue shifted, the light waves reaching us are more compressed, thus showing that the star is moving toward us. The last two methods of detection, together with some other discovery methods that we will not mention right now, have given us the thousands of exoplanets we know today. And we have learned something really fascinating. Planets are diverse. There are planets that existed only in our imagination, and some others that were not even imagined before. We will now illustrate the incredible diversity of exoplanets that have been found so far with some examples.
As you might know, last year's Nobel Prize in Physics was awarded for the first discovery of an exoplanet orbiting a Sun-like star in 1995. What you might not know is that that was not the first exoplanet to be discovered. Pulsars are the fast-rotating final stage that some big stars reach when they run out of their fuel. By analyzing the changes in the rotation of a pulsar, some astronomers discovered between 1992 and 1994 three planets orbiting one pulsar. This proves that there are planets orbiting dead stars. Another interesting fact is that the last planet of the three to be discovered, the innermost one, is the least massive of the planets ever discovered. Its mass is less than twice the mass of our moon.
Some decades ago, George Lucas imagined two sunsets in the fictional planet called Tatooine in his Star Wars saga, which you are probably aware of. Now, science has found that these kinds of worlds actually do exist. Kepler 16b is one such example. It is the first circumbinary planet to be discovered. Circumbinary means that it orbits two stars, which in turn orbit each other, as shown in the image here. It is a Saturn mass planet with surface temperatures somewhere between minus 100 degrees Celsius and minus 70 degrees Celsius. Before this discovery was made, it was actually thought that in order for a planet like this to exist around such a system in a stable orbit, it would have to orbit much farther away from its stars.
And there are even planets in systems with more than two stars. In fact, there is one close to us. Proxima Centauri, or Alpha Centauri c, is the closest star to the Sun. It is part of a triple system along with the Alpha Centauri AB pair, which it orbits with a period of 0.5 billion years. It is among the cooler and longest lived types of stars. And it hosts a planet, maybe more than one, of similar sizes and mass to the Earth, which also happens to be in the habitable zone. It is speculated that it might be habitable.
Most exoplanets we have found so far have actually much more extreme conditions than the bodies in our solar system. In fact, a good number of exoplanets have been discovered orbiting really close to their star. But HD 209458b, also nicknamed Osiris, takes this concept to the extreme. The planet orbits a star like the Sun, and its outer atmosphere is extended and heated so much by the nearby star that it starts to escape the planet's gravity. Hydrogen, carbon, and oxygen boil off in the planet's upper atmosphere under the searing heat of the star. The evaporation mechanism is so powerful that it's given rise to a whole new class of exoplanets which represent the cores of evaporated gas giants.
And talking about planets with extreme conditions, Kelt 9b is worth mention. The planet is in a close orbit around what is likely to be the hostess, most massive and short-lived star even found to host a planet. Kelt 9b is so close to this star that it is around the vicinity of the so-called Roche lobe. This is the area beyond which a planet cannot be stable and it's torn apart by the tidal forces of the star. It has been estimated that the planet has a temperature of 4,600 Kelvin. This is so hot that astronomers have found traces of iron and titanium in the form of gas in its atmosphere. And if you are not yet convinced that this is hot, this planet is so hot that its temperature is actually higher than the temperature of many stars. In fact, it's hotter than Proxima Centauri.
So we're all convinced now that planets come in a wide variety of flavors and they're abundant in the galaxy. But is one of them an Earth 2.0? When we search for an Earth twin, the first steps are to search for planets with similar sizes and masses to the Earth, orbiting stars with similar size and temperature to the Sun, at a distance similar to the distance between the Earth and the Sun. Interestingly, out of the thousands of exoplanets discovered to date, there are no more than just a few exoplanets with these particularities. But are we certain that they are Earth-like? Unfortunately, the answer is no. There are further conditions that need to be satisfied in order to call a planet Earth 2.0. Let us imagine that we just found an Earth-like candidate. What boxes does this planet have to tick for us to be sure that we found a true Earth analog? Well, between the characteristics that a planet needs in order to be called a true Earth 2.0, we have size and mass, properties of the host star, atmospheric composition, galactic neighborhood, moons, magnetosphere, and the list goes on. Planetary mass and radius are relatively easy to get. We do this via the two methods that we mentioned at the beginning of this talk. If we know the size of the star and we measure the amount of light that is blocked by the transiting object, we can easily find the size of that object, which is a planet. We, however, still have no idea about the mass of this object. Fortunately, the radial velocity method comes to the rescue by allowing us to get an estimate of the mass. Finally, when we have both the size and the mass, we can easily calculate the bulk density, which in turn allows us to speculate about the structure and composition of the planet.
Another really important aspect that we should check if the planet is able to host liquid water. If the planet is too close to the star, the planet will be so hot that any water on the surface will evaporate. On the other hand, if the planet is too far away from its host star, any water that the planet could have on its surface will be frozen. But there is an optimal region at which a planet will be able to host liquid water on its surface, the so-called habitable zone, or with a more conservative name, the temperate zone. A curious aspect about this is that the habitable zone depends on the host star. Cool stars have their habitable zone close to them, even for some of them the habitable zone is inside the orbit of Mercury. And on the other hand, stars hotter than the Sun have their habitable zones far away. If an Earth candidate were orbiting one of these hotter stars in the same distance Earth orbits the Sun, all of its water would be evaporated by now.
A really important aspect to note is that to search for Earth 2.0, we shouldn't focus only on the planet, but also on the star. The greater the mass, the shorter the stellar lifetime. This implies that the more massive the star, the faster it will consume its fuel. For example, a star about 30% more massive than the Sun would be in the final stages of its life if it were as old as the Sun. So a star needs to be small enough to have sufficiently long lifetime to allow for planets to evolve. While pretty average in terms of size and mass as far as stars go, the Sun is unusual in a sense that it is a quiet, not very active star. It does not flare up too violently or vary very much in terms of power output. This is not true for most stars, especially the less massive ones. So we would want the Earth 2.0 hosting stars to be relatively inactive like the Sun. A more massive star emits more high-energy radiation, which is harmful to life. On the other hand, a smaller star emits more low-energy radiation and thus neither emits in the wavelength range needed for photosynthesis. This would make it much harder for life as we know it to develop on planets orbiting such stars.
Most stars are actually found in pairs, i.e. stellar binaries, where two stars orbit each other. While it is possible for planets to exist in orbits around binary stars or other multiple systems, as shown before for Kepler 16b, this is not a favorable scenario for Earth 2.0, since the dynamics of the systems becomes more difficult to predict and can lead to unstable orbits. Thus, we will want Earth 2.0 to either orbit a single star or a star which is widely separating from its partners, as in the case from Proxima b. Just as a planet needs to be in the habitable zone of its star in order to be able to host liquid water, a star needs to be in the habitable zone of its galaxy. This means that it has not to be too close to the heavily populated radiation galactic core, where a strong potential radiation can sterilize any planet that might form there and perturbing its orbit. On the other hand, stellar heavy element content need to form planets containing similar elements to the ones here on Earth decreases towards the outer regions of the galaxy. So Earth 2.0 will orbit a star in the so-galactic Goldilocks zone, something like the galactic habitable zone. Another really important key test to search for an Earth twin is the planet's atmosphere. Earth's atmosphere is crucial since our atmosphere not only provides the air that we breathe, but it also absorbs harmful radiation from the Sun. In our solar system, we have examples of rocky planets with different atmospheric compositions. For example, Mars has a thin atmosphere with a totally different mixture of elements, and Venus with the most massive atmosphere of the terrestrial worlds.
Fortunately, we are able to study the atmospheres of faraway worlds. If we are lucky enough to be in the right place to see an Earth-like planet passing in front of its star, or the so-called transit, we could study the stellar light that passes through the planet's atmosphere, and we would be able to study the planet's atmospheric composition. Unfortunately, we need to see the planet transiting the star more than once, and for Earth-sized planets in Earth-like orbits, this would take years and years of effort.
Even if we find a planet that contains all the previous characteristics, we would like to play the game of a skeptic scientist and keep searching for more conditions. For example, a planet would also need a magnetosphere to deflect and protect it from dangerous radiation and high-energy particles it will inevitably encounter. A strong atmosphere is also a major factor in retaining a stable atmosphere. Recent studies have shown that Earth evolution will be totally different without our moon, so maybe we can search also for moons around the Earth 2.0 candidates.
So we have found more than 4,000 exoplanets, but we have not found an Earth 2.0. Does this mean that our planet is unique?
Well, not exactly. We also need to be aware that even if there are plenty of Earths out there, they are hard to catch. Our detection methods are based towards detecting big planets in short orbits, and in comparison, our Earth is a small planet with a relatively large orbit.
As people who are actively involved in the search for other worlds, we can testify to the level of challenge that finding another Earth truly is. Being a member of research consortia and international collaborations is a key prerequisite for improving our chances of finding Earth 2.0 because it takes cross-disciplinary expertise to accomplish this complex task.
The good news is that this is a wonderful time in which technology has started to catch up with our imagination. Present and future instruments and telescopes, such as Gaia, Plato, Espresso, will allow us to detect thousands of new worlds in the coming years, and tens of them will have characteristics similar to the Earth. Meanwhile, some other instruments, such as the James Webb Telescope and Ariel, will allow us to test the most stringent constraints that a planet has to meet in order to have the honor of being called Earth 2.0.